You are listening to the Wi-Fi Ninjas podcast, where we talk about wireless technology. Here are your hosts, Mac Daring and Matt Starling.
Hello everyone, and welcome to the Wi-Fi Ninjas podcast. Matt and Mac here. How are you, Mac?
Never better. I'm surprised that you keep on asking because like every week or every 2 weeks is the same answer. How about you?
Yeah, no, very good. Excited to be recording another podcast with my good buddy, yourself.
The pleasure is all mine, my friend. How many podcasts have we done on our own now?
Back to back in a row? I think this must be our fourth one.
Wow. I don't think it's ever happened before. And this is like a brand new environment for me as well, guys. So I've spent like last 5 days, 15 hours a day creating working on a new equipment in my studio. So now I'm looking at Matt and it looks like I'm looking directly in your eyes because I have a teleprompter. But it's so difficult to set it up correctly to have everything. It's like, oh my God.
Yeah, it's not like us to play around with our setups at all, is it?
No, not at all. Like, we don't do it, right? I hate it and love it at the same time. It's like I love playing around with these toys, but I would like it to be done now, done and dusted. But it's never going to be the case, I don't think. It's like you finish it and then next week you have a new idea and then you have to do it all over again.
Yeah, so if anyone's watching this podcast now, by the time they watch the next one, it would all have changed again for you, for me, and I wonder what it'll be like.
Yeah. I've lost my ultra-wide screen. This is difficult for me.
I'm not sure how you've decided to give that up, to be honest.
It's not possible to have a setup with an ultra-wide screen in front of you, teleprompter on top of it, because the camera is going to be too high. So it would have to be to the side, which will make it not ergonomic. Yeah. And it's not acceptable.
Yeah. Well, anyway, we can spend multiple podcasts talking about our setups and our challenges and, the unique things that we've come across. So maybe we'll save that for another episode down the line. But today, what we want to be talking about is a modulation. So we're going to be spending the next however long for the rest of the podcast talking about the different types of modulation, what we can expect from those types of modulation, and then we'll be giving some real world examples.
Sounds like a plan.
Yeah.
So the modulation, let's do like a quick intro to what it's going to be. So guys, Wi-Fi is a protocol that operates using what medium? We don't have cables, right? We have just radios, electromagnetic energy around us. And it's not only us, it's not only Wi-Fi, it's all the other devices that can be sitting in the same spectrum band, but not necessarily using the same protocol. So we have our 802.11 modulated Wi-Fi signal, and we can have analog cameras, microwaves, movement sensors, whatever else can be living in the same ISM free-to-use band. And if you pay attention, you will notice that I said 802.11 modulated signal. What do I mean by modulated? And that's exactly what we are going to talk about here. How do you modulate the signal to carry ones and zeros using electromagnetic energy that is all around us, right? We are using air as the medium. That's very important to understand and not too easy. Well, actually, my mind was blown away when I was first listening to, I think it was Jerome Henry again, talking about the modulation. This has made me fall in love in Wi-Fi. And I wanted to dig deeper after listening to all these beautiful videos. And that's exactly what we're going to cover. Anything to add, Mr. Matthew, before we jump in?
No, so just to be completely truthful and honest here, I didn't listen to it once, watch it once, and then get it. I had to watch it multiple times, draw it for myself, watch it again, read about it again, before it really started to sink in and for it to make good sense to me.
Yeah, especially if you look at, I don't know, Keith or Francois doing all this nice fancy drawing with the sinuses and whatever. It's like, it looked very complicated, but it's really not that complicated, is it? Once you grasp what it is about. So basically, guys, the modulation is using a physical phenomenon of electromagnetic energy to put ones and zeros into the air. And what I mean by electromagnetic phenomena, you can either send signal or don't send signal. So your radio can be on and off, and the receiving end will be able to pick that up. And then every some number of microseconds, like let's say every synchronized slot time, your device will be able to just see if the radio is on or off. If it's on, it means 1. If it's off, it means 0, something like that. This is the most basic modulation, the physical phenomenon that we can use, radio on or radio off. Before we jump into the real modulation schemes, let's spend a second talking about what are the attributes that we use to describe electromagnetic wave. And we are going to be using these attributes to do a modulation. So first, it was the baseband. It was just the radio on or off. Mm-hmm. The second one is the amplitude, right? So amplitude is, let's not call it a power, but it's the amount of the energy that the wave is carrying. So if it's a strong wave, then the amplitude is high. If it's a not too strong wave, then the amplitude is low. So it's like a loudness. The amplitude is like a loudness. And then we can say, if I'm very loud, then it means 1. If I'm very quiet at the slot time, then it means 0, or the other way around, depending on the protocol. So we have 2 now. We have discussed the baseband, radio on or off, and amplitude. Is it loud or is it quiet? Of course, there can be more states than just loud and quiet. It can be very quiet, somehow loud, loud, very loud, extremely loud, and so on and so forth. Every time we use the amplitude and we want to differentiate between the amplitude level, we have to be more precise. And we will talk about the precision SNR later on. So Matt, what's the next attribute that we can use?
Well, I'm going to say phase shift keying, but I'm not sure if you wanted me to talk about the frequency modulation, where you could be flipping between frequencies to change if you were talking about a 1 or a 0. But do we use that in Wi-Fi?
Well, no.
So you can, in other technologies, flip between frequencies to change if you want to be sending a 1 or a 0, but that's not what we do in Wi-Fi. So I'm going to skip that one and I'm going to go to PSK, not to be confused with the pre-shared key attribute for when you're putting in the password to your lovely Wi-Fi network, but PSK in the term of phase shift keying. So when we're going to be modifying the start of the wave, or how we've been receiving the wave, if it's at maybe a 90-degree phase angle, is it 180 degrees, is it 270? So we're going to be modifying the phase of the wave now to decide to change if we want to be sending a 1 or a 0. But my question to you, Mac, what do you do if you are to add amplitude shift keying and phase shift keying together?
Ooh, we're diving a little bit deep now, right? So you're probably talking about QAM, but before we go there, shall we start with something a little bit easier, perhaps? So let's discuss the slot times so we can grasp when the modulation is coming. So let's say in the OFDM, in Wi-Fi, we have a concept of a slot time, which is 9 microseconds. And every 9 microseconds, you can code something into the air. So there can be a signal or no signal. It can be fast or slow using the frequency. By the way, we don't use neither baseband signal and we don't use frequency, as Matthew has stated. And then it can be loud or quiet, and it can have a different starting point, different phase. So phase is like the... How do you say that so it's correctly physically? It's the 2 alternating currents and the difference between them?
Yes.
Or when you start at 0 and then you go to 90 degrees and then down to 180 and then down to 270 and then back up to 360. When you start at 0, that's your 0 degrees phase. When you start at 90, that's your 90 degrees phase. And in order to understand phase a little bit better, it was the most difficult for me to understand phase. Everything else is pretty much easy or self-explanatory. Think about the radio wave, a sine wave that we use to describe our electromagnetic energy, our signal in the air. Think of it not as a 2D sine wave. Think of it as a 3-dimensional object, like a spiral stuff. If you have like a Philips Hue vintage bulb, for example, that's how the sine wave looks when you look from the orthogonal view onto the wave. And then when you look like not from the side but from the front, then it's just like a circle. And then you have a point going around the circle from 0 degrees to 90 to 270 and 360 again. And then it starts again from 0, and so on and so forth. So that's the phase. And then each of these attributes, it can be read by a receiving end at the slot time every 9 microseconds in OFDM transmissions. And that's what we use. So let's start with the very basic modulation scheme. Let's start with something called the BPSK. I know, Matt, that you were bursting to talk about BPSK, so go for it.
Wow, thank you so much for giving me the slowest modulation constellation to start with. But okay, let's get into it. So BPSK, so this is the most basic form of modulation that we'll be using in Wi-Fi. So in Wi-Fi, our modulation schemes, they can either be very simple, not so complex, and they'll work, but not go very fast. And you'll see when we get up to the more complex modulations that we're going to talk about in a few moments' time, is that the more complex, the harder the modulation is. So if you compare it to a language, if it's a very easy language, we can talk nice and slowly, we can understand it. But if we think about the modulation when it becomes more complex, it becomes like a very complicated language and we can talk very fast. So starting with BPSK, we can send a maximum of 1 bit at a time on the RF medium. So this means that we are only ever going to be sending either a 0 or a 1. So it's extremely simple, but it's very robust. So the thing with Wi-Fi is that it very rarely actually breaks. So Wi-Fi will not actually really physically break. It's just going to go very slow. That's what Wi-Fi is designed for. If this doesn't work so well, then it kind of drops its modulation, and then it goes to use the most robust modulation, which is BPSK. And we can still demodulate and work using BPSK with an extremely low signal to noise ratio. Very quickly. When I receive a Wi-Fi signal, that signal strength that I received that is compared to what is the noise floor. So the calculated noise floor. Let's say in this example, the noise floor is at minus 95 dBm. And we receive a signal at minus 65 dBm. That will give us a 30 dB SNR, because the difference between minus 65 to minus 95 is 30. And typically in Wi-Fi, we want to be achieving a minimum of 20 to 25 dBs at least in pretty much all situations, but especially if you're trying to do voice or video over Wi-Fi. So coming back to BPSK, at what SNR value that works at, we can still achieve BPSK at 2 dB SNR. So very, very poor signal quality. So very low SNR. Yeah, very, very low. It's still going to work. So that means if you've got a noise floor of minus 95 and you somehow have a signal with minus 93, that 2 dB difference, you're still going to be able to do BPSK.
And minus 90 something dBs, like dBm, this is such a low power level. It's like when you say 1 divided by 10, divided by 10 and by 10 by 10 by 10 by 10 again, like 9 times. That's where we are getting to if you wanted to describe the energy levels in milliwatts, that's very low.
Yeah. So the only concept that we haven't spoken about right now is the EVM, which stands for error vector magnitude. So the way I like to describe the error vector magnitude is
Before we say anything, I'm almost sure that you're going to use football for that.
Of course, that's how I like to explain it. I'm a football kind of guy, so a lot of listeners will understand football. Even you, Mac, you don't really watch football, but you still understand some football things, right? So don't hurt me and not let me use my football analogy here. So anyway, before Mac rudely interrupted me and said I was going to be using a football analogy for EVM boxes, he is absolutely right. I am going to be using a football analogy. So let's say, for example, what football team do you support, Mac?
What football teams are there?
Well, maybe you support. Let's say it's the internationals. Maybe it's Euros, and you're obviously Polish, so you want to support Poland.
I don't think I would, man. It's like they really suck at football.
Okay, right. Who are you supporting in the internationals then? You're gonna be England?
Probably higher chance of me supporting England. Yes, of course.
Okay, fine. Right. So, Mac, it's the cup final at Wembley. You're playing for England somehow, even with your Polish nationality, you managed to get into the English team somehow, and we've won a penalty, and you're stepping up to take the penalty, and you can see the goal in front of you. So you've got the goal in front of you, and then you've got the goalkeeper standing in the goal. And I say to you, Mac, to score the goal, all you have to do is put it somewhere to the goalkeeper's right. Doesn't matter where it goes on that right-hand side, it's going to be a goal. As long as you shoot and the ball goes into the right-hand side of the goal, anywhere, low, high, medium, we're going to be scoring. So how does that relate to the EVM box? Well, if you take the same scenario that we are going to be sending either a 0 or a 1, our EVM box is the equivalent to that one whole half of the goal, is that if we shoot anywhere, up, down, to the side of that goalkeeper, the radio on the receiving end is going to be able to decode and understand that we're trying to send a 1. But if Mac slips as he runs up, or he scuffs it and it goes to the keeper's left, and that's going to be in our 0 side, and it's not going to be able to be decoded or understood that we were trying to send a 1. So we've got a very large target to aim at when we're using with BPSK. So our error vector magnitude box is the largest that it's going to be out of all of our modulation constellations. How are you feeling, Matt? Confident that you can take your penalty and score?
Not sure I would even be able to kick the ball in the right direction, man. I can try. We can try it out next time we are together. But we'll need to have a lot of beer before me doing it. However, I will have to be careful, because every time I play some ball-related sports, I end up with a twisted ankle or something like that. So I have to be very careful with that. Maybe I can't even run on the grass, man.
Maybe you can be the goalkeeper then in this scenario, and I'll be taking the penalty.
Oh yeah, man! It's like I'm so fat, I won't even have to move around to block most of it.
And then add your dodgy shoulder into the mix as well.
I don't need to use my shoulder, right? It's like I'm so fat. Even with my, without my shoulders, I would still be able to be a decent goalkeeper.
Okay, so that's binary phase shift keying, and the clue here as well is, in the name BPSK. At the moment, we are just using phase shift keying. Yeah.
So left or right, that's it. Yes. And we are just using BPSK, binary phase shift keying. So it does not matter if your phase of your signal is at 0 degrees, 1, 2, 5, 10, 50, 100, or 179. It still means 1 bit, 1. If it's like anything bigger than 180, then it means 0, or the other way around, doesn't matter. But you get the idea. You don't have to be precise. And that is why the SNR, signal to noise ratio, can be that low, and it's still going to work. So Wi-Fi will pretty much always work for as long as there is a signal there. It will never be too fast in that situation, but it will work.
Oh yeah,
nevertheless.
Sorry, maybe we should mention what the speeds what data rates we can achieve when using BPSK. So it's usually going to be somewhere around 6 megabits per second. I think potentially get out to around 11 megs.
Yeah, just looking at the table. So guys, if you want to take a look at how different modulation schemes they affect Wi-Fi throughput, Wi-Fi data rate, MCS rate, then look at mcsindex.com. It's the website called the mcsindex.com, and you will be able to see everything that is achievable there, based on modulation and phi, the generation of Wi-Fi.
It's going to change on regarding what is the channel width and the standard of Wi-Fi that we're using, but just to give kind of some sort of example there.
Yeah, so another example with BPSK, if you use AX, okay, or it can be pretty much anything, doesn't have to be even AX, it can be HT. HT phi, it stands for high throughput, is 802.11n from 2009. And if you start bonding your channels to 160 megahertz, this is the best channel width for your high density usage in the corporate world, isn't it, Matt? Then you can have up to 65 megs using BPSK. So just sending 1 or 0 at every slot time. It's a lot. And guys, by the way, I'm joking. Never use 160 megahertz under any circumstance, even at home, and especially not in high density environments. What do we want to use, Matt, in high density environments where you have tons of neighbors and neighbors of your neighbors?
The widest channel until you can't.
Okay, which is typically?
Usually in a high density deployment, especially if you're in a built up area in a city, lots of offices, multi-tenancies, then guys just stick with 20 megahertz wide channels.
Such a good tip. And on 20 megahertz channels with like one spatial stream, you can go up to 7.2 megs. Okay, so typically with two spatial streams devices, and most of the devices, even mobile devices on the market today and laptops, there will be AX two spatial streams devices. They would be able to achieve on 20 megahertz channel twice that throughput, so 14.4. I don't remember that, by the way. I'm sure that Peter Mackenzie does remember all of these values. I don't.
As well,
So
right?
I have
He's memorized this table.
Yeah, memorize this table. How many values do we have? There's like memorizing 8.11n might be possible because for every single spatial stream, you go from 6.5 up to 150. But how about the AX, man? It's like
it's too much. Too much, right?
I wanted to count like the vertical amount of, well, I wanted to count the columns and rows to come up with how many different data rates available we have in AX, but this will be tens of hundreds, right, of different data rates. So enjoy memorizing that.
Yeah. So over to you, Mac. Then, what's the next form of modulation in Wi-Fi?
Okay, so the next modulation in Wi-Fi is something called the QPSK. So Q now it stands for quadruple PSK. It was BPSK before, binary PSK, 1 or 0. Now it's quad PSK, quadruple PSK. It means that every slot time you can send not just 1 or 0, you can use 2 bits at a time. You can send 2 bits at a time. It can be either 00 or 01 or 10 or 11. So you can be twice as fast. But at the expense of being twice as fast, it goes a little bit more complex. It's like twice the complexity here, not 4 times like with QAM. It's twice the complexity, right? So the EVM vector. So now when you want to score a goal, I'm going to use your analogy. I can't believe that I'm talking about sports here. You not only have to be trying to shoot towards the left or right of the goalkeeper, but also you have to be more precise. If you want to encode 00, you not only have to shoot to the right, but also to the top half of the right sector.
Yeah, so effectively now, the goal is split in 4.
Yes, the goal is split in 4. So it's still fairly easy to achieve if you have math skills, of course, because if I stand like how many meters away from the goal do you stand? 11 meters away?
I was going to say, yeah, it's around 10 to 12 meters, I think you are for the penalty shot.
I wouldn't be able to do it again, but for math, it will still be fairly easy to shoot in one of the corners of the goal. And now with 2 beats at a time, we have.
I can really feel a video coming on here. We've got to go hire a football pitch and get a goal, and we're going to have to take something to split up the goals, and we're going to have to put 1s and 0s and 0-0 and 0-1, and then take shots, actually taking a penalty to see how many times we can shoot accurately.
I can add the split in post-production, man. That's not a problem.
Okay.
Let's do it. Let's do it.
I can feel it. I can feel it coming on. I think it'll be a good video.
Yeah, well, for you maybe. For me, it'll be more of a laugh at poor Mac, but yeah, let's do it nevertheless.
Okay.
Yeah, so now you need just around 5 dBs SNR. If you have more than 5 dBs SNR, then you will be able to achieve QPSK modulation. And 5 dBs is still extremely low. So using the same example, if you have noise level at neg 90 dBm and you have a signal level like the RSSI modulated 802.11 signal at neg 90, it's very low, extremely low. You can have BPSK. And this will give you like 12 megs per second on that low SNR. If you want to go faster, then you will need to have slightly higher SNR. So at 10 SNR, 10 dBs signal to noise ratio, you will be able to use a little bit more advanced coding mechanism, which means for the amount, when you send some bits over, the amount of bits carrying data will be higher with higher coding schemes. So let's say if you have a coding of 1/2, it means that every 2 bits sent, 1 will be carrying data. If you have coding 5/6, it means that 5 out of 6 bits sent, 5 will be carrying data, and then you can go faster using the same modulation scheme. So with 10 dBs, you will be able to get 20 megs, but 20 megs is for what? 20 megs using QPSK is for, I would say, 20 megahertz channels, channel short guard interval. I'm looking at MCS index again. It will give you 14.4. If you use 2 spatial streams and QPSK, it will give you the speeds, the throughput of between around 30 to around 40 megs per second. So the real speed with, let's say, AX that is better at handling the protocol overhead, you will have like 75% of your throughput will be your real speed that you should be able to achieve. So it's not the fastest in the world, but it's getting there, right? Like 20, 30 megs is getting decent-ish for a single device on a Wi-Fi network. So that was BPSK, and now it was QPSK, 2 bits at a time, every slot time. What's next, Matt?
So now we're going to be stepping into the world of QAM. This is the first time now that we're going to be talking about QAM, and the very first modulation constellation that we'll be using is 16 QAM, and QAM, QAM, stands for Quadrature Amplitude Modulation. So
or about to what analogy you are going to use for that?
Yeah, so this is now when we're combining amplitude shift keying as well as phase shift keying. So we're using the 2 types of methods here to create what's called 16 QAM, and now it starts to get a little bit more complex. So we're using QAM for the first time, and we can now send on the radio 4 bits at a time. So if we wanted to send a 0010, we can, or we could send 4 zeros, 4 ones, for example. We can now get roughly around twice the amount of throughput and speeds to what we had before previously with QPSK, but it starts to get more complex. And even though we're saying it gets more complex, it's actually still pretty easy to achieve in Wi-Fi. If you've got a well-configured Wi-Fi network, this should be theoretically very simple for you to achieve, because we still only need to have around 10 to 15 dBs SNR value to be able to achieve 16 QAM. But now when you're thinking about our EVM box, it gets smaller, so it's more complex. We have to be more accurate. So if you were to be taking a penalty at Wembley on the 90th minute for a cup final, you're going to have to be putting in the very top right hand corner, and that corner is going to be very small. So maybe it's a good time to switch over from being accurate with a football pitch, and maybe it's better suited for a dartboard. If you're throwing,
I still think it's a spotless example for the football, man. It's like you have to hit like 1/16 of one quadrant of a goal, but not only that, you now different. So this was the amplitude, right? Like the left side or the right side, or left top or right bottom. So now you're looking at 1/8, I think, of a quadrant to be precise there, or 1/4 of a quadrant with QAM 16. 1/4 of the quadrant.
Yeah, 1/4.
So it's not too difficult. Well, it's getting difficult, but for Matt, it's nothing, right, to hit that. But this quadrants, it's just the amplitude. Now we are also shifting. Well, this was just phase. Now we are also shifting amplitude. So not only we have to be shooting into the right direction, but also we are adding amplitude. So add this direction with a strong signal, or at the same direction with a low signal strength. So you hit the ball very hard, or you hit the ball not too hard, right? And shooting exactly in the same way, in the same direction. So we can still use that analogy, right?
Yeah, I like it a lot. It's one I use all the time. It's my favorite. But basically now we have to be more precise, more accurate. When we're shooting, we have to pick our right hand side. We have to pick if we're going high, if we're going low, and then we have to pick a quadrant out of that corner as well. So when we're taking our penalty now, it becomes harder to score, but we can go faster.
Yeah, that's what's happening. So the complexity of the EVM, it's 4 times more complicated to have gain of what? Twice the speed, right? So you have 4 beats,
Roughly, yeah.
encoded at any given time now, every 9 microseconds potentially, but the EVM is 4 times smaller. So you still have very good gain in speed and throughput, but that's at the price of massively increased complexity. Okay, so what's the SNR that we need to achieve 16 QAM?
It's around 10 to 15 dBs SNR.
So it's still nothing, right? So with the neg 95 noise, it would be what?
Minus 85, minus 80, yeah. Between minus 80 to minus 85, we can now achieve 16 QAM.
Yeah, so minus 80 is nothing, right? Like, yeah.
Where we can get up roughly somewhere between 25 to 50 megabits per second speeds with that poor quality of signal. When I say poor quality, but not as good quality as what we have come to expect in Wi-Fi.
Yeah, what you target to have with a proper, not only configuration as you've mentioned, but also like a proper design. So to achieve all these beautiful modulation schemes faster and faster, you need to have a proper design or sit very close to the access point. If you have crap design and you want to use advanced modulation schemes, you have to be very close to the AP. So some users will be talking fast if they're close to the access point, and some users associated to that access point from far away will be getting maybe QPSK. So when they talk, they will be slow, and they will be affecting clients that are using QAM modulation, right? Because they take more airtime to send or receive data.
Definitely right. So that's what a good thing that you said there is that basically the stronger the signal strength that you have means you're most likely going to have a higher signal to noise ratio, which means you can then use a more complex modulation, which will therefore then mean that you can talk at a faster speeds, so therefore achieve a faster throughput. That's the whole aim of Wi-Fi, what you want.
Yeah, basically that's what you want in Wi-Fi. So if you know that one sentence, then you know Wi-Fi, right? Just faster speeds. Speaking of faster speeds, we are switching to QAM 64. So that's the modulation scheme introduced in 802.11n. So Wi-Fi 4, that's where we could use 64 QAM for the first time. And 64 QAM is just more of the same. We can now encode 6 bits at a time, every slot time. So we are up to 6 from 4. So we don't have like twice the gain in the throughput now. We don't. The data rate gain will be 50% and not 100%. And it's still 4 times more complex to achieve that when compared to the previous modulation. So it's it's getting quite complex, but the gain is not as massive. So 1.5 times better throughput is still better than no gain, but it's nothing to write home about. However, we are targeting to, the design best practices say that you don't want to drop below QAM 64 everywhere where you expect to see a signal strength, signal coverage inside your carpeted office space. That's for the carpeted offices, like decent density. You don't want to go lower than 64 QAM. So 64 QAM, it now allows you to go for a single spatial stream device. I think, let me not think because I'm not good at that. I will take a look at the MCS index. You can go up to 150 megs per second for a single spatial stream device of data rate. That is not throughput. This is just a data rate.
Not too bad, right?
No, it's not too shabby, and I don't think. But that's on 40 megahertz channel. Channel bonding was introduced in N. So with 40 megahertz channel, you can go up to 150. What channel width are you using in your environment, Matt?
Right now, 20 megahertz.
Yeah. 20. Okay, I am on 40 megahertz. So I could go with my Mac Mini. I switched from MacBook Air to Mac Mini. I would be able to get 300 megs throughput with QAM 64 to spatial stream device using 802.11n. Okay.
So Mac, I think you raised a good point here without even realizing it. So how do the listeners start to figure out and work out what they're capable of, their devices, what they're capable of doing? So how would they, if they wanted to come look at the mcsindex.net or .com, this is a pretty hefty table that we're looking at right here. How do our users know what their different devices are capable of doing? So what is the criteria that we need to know to be able to understand what our devices can actually achieve?
Yeah, great question. So if you want to calculate to understand what you can achieve when it comes to achievable maximum data rate that your device can pull off, you need to know how many spatial streams your device supports. So typically the devices will be supporting 2 spatial streams today on the market. What is the PHY, so the generation of Wi-Fi that your wireless NIC can do? Is it N, Wi-Fi 4, AC, Wi-Fi 5, AX, Wi-Fi 6? Because this will change the modulation that you can use. Let's say we are now talking about 64 QAM, and that was achievable back in 2009 with 802.11 and Wi-Fi 4. Then in 2014, we had AC generation like Wi-Fi 5 coming out, and it was using 256 QAM maximum. And now AX, it can use up to 1024 QAM. So that will change what your device could achieve.
How many times have you been asked this question, Mac? When you're designing a Wi-Fi network, when you're implementing a Wi-Fi network, when you're troubleshooting a Wi-Fi network, when your friends come over, when your family come over, the question, how many times do you get asked this question, Mac? Is how fast can the Wi-Fi go?
Yeah, the answer is like Sam Clements style, right?
Yeah, of course.
It depends.
Every time. And that's why I say to the students in the ECSE class, that if you ever, I was like, who gets asked this question? You know, when you get at your friend's house, your family's house, and you're setting up the Wi-Fi for someone, or you're going on site and you're installing it, you get your mum, your brother, your cousin, the customer, and say, oh man, we've just put in this amazing, great new Wi-Fi infrastructure. How fast can we go on Wi-Fi now? You know,
I think it's easy. It's like, take a look. If it's just Wi-Fi 5, so you bought a router 7 years ago, take a look at the box and what this tells you. Typically, you will see something like 7 gigs. So yeah, my Wi-Fi can do 7 gigs, man. It's like, it's so fast. Yeah. Not like your old school cable. It's just 1 gig, right? I can do 7 of these cables, man, in my access point. But then honestly, it depends. In order to be able to achieve 7 gigs, standard, that's supported. But not only you will have to have very high SNR to support like 256 QAM, so even one level up from what we've discussed so far, but also your device needs to be able to support 8 spatial streams. Ooh. And 8 spatial streams is like using 8 transmitting radios and 8 receiving radios, so MIMO, multiple input, multiple output, where each of the radios will be transmitting and receiving different information at the same time. So every slot time you will have 8 guys talking on top of each other, trying to have a conversation that will be very difficult to decode on the receiving end. So this is not only CPU heavy, but also powering up 8 radios is very battery heavy and it's mathematically complicated. So it will be CPU duty cycle heavy. It's just not achievable, right? I don't think I've seen a single device on the market that has more than 4 spatial streams. And this 4 spatial streams, it was a while ago. And the trend is reversed now. We don't tend to try to pack as many radios in the devices. We just want to keep it to minimal practical,
efficiency.
Minimal practical approach. How do you say that?
Yeah, efficiency maybe.
Point, access point, they will be able to support more spatial streams, typically like 4 or even 8. But the devices, they will be typically in AX world 2 spatial streams devices. So when you take a look at the fastest available speeds with 160 megahertz channels now in 802.11n, or actually N won't be able to do 160. So if you have this Wi-Fi 5 device then, and you tried to be super smart by saying you have 7 gigs, if you want to be more practical now, your devices, if they support 160 megahertz, and if your access point can do that as well, you are now down to 1.7 gigs. And actually, I have seen 1.7 gigs when I was sitting close to 160 megahertz enabled home Wi-Fi APs. It's not like you need that, right? Because your cap typically at this point will be your cable, which is typically 1 gig. Yeah, I think that's everything that I wanted to talk about when it comes to the attributes that you need to understand what your device is using in order to be able to specify what throughput can be expected.
Yeah, so that's the attributes. One thing for Windows users, let's start with Windows guys or girls, if you're using the Wi-Fi. If you want to start working out what is your MCS rate, you need to go into you need to understand all of the attributes that Max just said. So what is the physical standard of Wi-Fi that your device is capable of? How many spatial streams? What's the maximum channel width? And then what you need to do is open up a command prompt, and then you need to type in, I think it's net sh w space wlan space show interfaces. I'm
Still remember that, man. I'm impressed.
Yeah, I'm not a Windows user anymore, but I'm pretty sure it's net sh space wlan space show space interfaces. And then what that is going to give you is a whole bunch of information, but what you're going to be looking for there is your TX rate. So what is your transmit rate? You then need to take that number, come back over to your mcsindex.net.com, and you now need to go and find that number inside of the column relating to how many spatial streams. If you're 1 spatial stream, 2 spatial stream, 3 spatial stream, 4 spatial stream, if you're 11N, AC or AX, then you can come along, see where your transmit rate is inside of that nice table, and then scroll your mouse across to the left, and then you'll be able to see what is your MCS index number. So yeah, nice and simple really. It's a bit more difficult a little bit more difficult for Mac users, because what you need to do is go over to your Wi-Fi icon, and then just before you click on your Wi-Fi icon, you just need to hold down the Option key, and then as you click on the Option key, you're then going to see a whole bunch more information in your Wi-Fi bar, not in your bar, but the drop down. You're going to see IP address, all that kind of stuff, and then you look down, you're going to see your number of spatial streams, your transmit rate, and you're going to be able to see your MCS index. Either that, or you can install Adrian Grandos's Wi-Fi signal tool and have it showing nicely in your toolbar. So yeah, a little bit more complicated for Mac users than it is Windows users. I'm joking, by the way.
So that made me realize that I am associated actually to the access point on a different floor in my house. I am connected to the AP on the ground floor. That's where I started configuring my new Mac Mini. And now I'm on the first floor and I'm still connected there. Stupid Mac. But yeah, an MCS index, just by specifying the MCS index, let's say the fastest available MCS index in AC will be what?
9.
10? Is it 9? 9. 9 AC, yeah.
It's a little bit, there's a little bit confusing there, right? So, because if it's on 11N, it goes from, it starts at 0 and then goes to 7 if you're 1 spatial stream. And then when you go to two spatial streams, it then continues on logically. It goes to 8, 9, 10, 11, 12, 13, 14, 15.
That's N.
Yeah.
Yes.
Yeah.
N. So 11.
But then you get to 3 spatial streams and it continues on from 15. It goes up to 16 through to the next round. But with 11AC and 11AX, it starts at 0 for 1 spatial stream, goes up to 9 for 11AC, 11 for 11AX. And when you go to 2 spatial streams, it doesn't continue on, it goes back to 0. So it then goes through 0 to 9 or 0 to 11 again, till you hit the 3 spatial stream, and then you start again from 0. So that is a little bit confusing, so just watch out for that when you're first having a look at the chart.
Yeah, but when you do know your MCS rate, so let's say I'm on MCS rate 9 now, I know that I am associated to the access point that does AC Wi-Fi 5, and I know that I am using 40 megahertz channels. So just having these 3 bits of information, I can translate that into the throughput that I should be able to achieve. So just looking at the MCS table with all the information that I have just provided, 2 spatial streams, 40 megahertz Wi-Fi 5, I can go up to 400 megs. And when I hit the option button and hit my Wi-Fi symbol in macOS, I can see exactly that. My data rate is 400 megs and MCS rate is 9. So MCS rates, they are just used to quickly describe multiple different things with just one number. So when I say I'm on MCS index 9, we know that MCS index 9 will be either up to 200 megs on 1 spatial stream or 400 megs on 2 spatial streams for Wi-Fi 5. We know that, right? And then we don't have to keep on specifying, oh, by the way, I am on AC and 40 megahertz and short guard interval, and I'm using QAM 256. I don't need to say that. Encoding 5x6. All you need to say is 40 megahertz AC, MCS index 9, and everything is included in that information. Right?
Yep.
Right.
Right.
Absolutely.
Perfect. Okay, so I know we'd mentioned 256 QAM and 1024 QAM as an overview there, but we didn't really dive into the differences because we was talking about 64 QAM and then we got a little bit excited and sidetracked. Not like us at all, but we did when we're talking about the MCS index and the requirements and criteria that we need to know. So moving on to the next type of modulation that we were talking about previously before, which is QAM 256 or 256 QAM, however which way around you like to say it. This was introduced with 11AC, so Wi-Fi 5, and we can now send 8 bits at a time. So we get more throughput, faster data rates, but you have to pay a price here, because if you want to achieve these faster speeds, our target, going back to our taking our penalty in the 90th minute at a football scenario, the part of the goal we have to aim at now is super small, so we have to be extremely accurate when we're taking our shot, when we're going for
1/64th of a quadrant.
So if you imagine the goal split in 4 now, so if you draw a line down the middle of the goal, and then a line across going vertically, and then another line going across horizontally, and you just talk about one quadrant of each parts of the goal now, would you say it's 1/64th?
Yeah, of a quadrant, or 1/256th of entire goal.
Yeah. So yeah, out of a quadrant, we've got to be aiming at a box that is the size of 1/64th of that box. So
and also, this is just a phase, right? Then you will sometimes have to differentiate between up to 8 different amplitude levels. So if it was extremely silent, and then going to very, very strong signal. So not only phase, 256 different possibilities there, but also for each phase, up to 8 different possibilities for the amplitude. So it's quite complex. 256 QAM is quite complex. Having said that it's complex, it's still achievable, like rather easily.
Yeah,
I have to be very far away from the access point to drop below QAM 256.
Yeah, so the signal to noise ratio that we need to be achieving here at a minimum really is around 30 dBs. So in most scenarios, just in your home environment, if you're not too far from your access point, you should easily be able to achieve this theoretically.
So you say not too far from the access points. I'm talking about the other side of the floor, one floor down. So I'm going for like 3-4 different floors plus a ceiling, and my RSSI is now neg 60, okay? And if my noise floor is, let's say, around neg 92, I have already exceeded this 30 dBs or better. So I will have QAM 256 in this situation. And that's what I do have. I have QAM 256 on my laptop. Not only that, I am using the fastest available MCS rate, so fastest available coding for that modulation scheme. And I am really not like close to the access point. So I would say with a proper design, you should be able to achieve QAM 256 everywhere in the carpeted office space, like everywhere. I kid you not, it's doable. Okay, let's take it one step further. So now in QAM 64, we had 6 beats per second. Now we have 8 beats per second. So the gain in row speed or throughput or data rate is just 30 something percent. 1/3, right? Is it 1/3, 1/4?
It's about one. Well, you can throughput wise, we can achieve about 1.3 times theoretically.
Yeah, and still it's 4 times more complex than before. So the gain is getting smaller, and the complexity, it rises at the same pace. So it's quite complex. They say that it's not that achievable, but based on our experience, you should have QAM 256 everywhere easily, which brings us to talk about QAM 1024.
Ooh.
So QAM 1024 is introduced as part of the AX Wi-Fi 6, okay? And I've heard multiple jokes about people saying that you need to be sitting on top of your access point to get QAM 1024. Actually, I think if you sit on the access point, depending on who sits on the access point, if I sit on the access point with my fat bum, I don't think I will be able to get QAM 1024. But if I stand, and this is our like real field tests, if we stand like 11 meters away from the access point with clear line of sight using a mobile phone, then we are still getting 1024 QAM. And that's, again, up to 11 meters with clear line of sight. When you are sitting in your office, what is the chance that you will have an access point closer than 11 meters away from your desk? I would say with a high-ish density design, it's close to 100%, which means that most of the floor, with correct design, again, will enjoy QAM 1024, which many people say is not achievable. It won't be MCS 11, that is the fastest available MCS rate. It will be MCS 10, 11 meters away, but it's still QAM 1024. It's still plenty fast. Now, we had MCS 11, fastest available MCS rate on AX, up to 7 meters away from the access point. So you would need to have APs more than 14 meters away from each other in the open space, carpeted office space, not to achieve highest available MCS rate. Now, to put it into perspective, when I'm connected to the access point, to my access point on my floor and my landing just outside of my office, I still have to go through two around 3 dB attenuation walls. I am around 4.5 meters away in a straight line. So I don't even have line of sight. And I am sitting most of the time on a sunny day, all day. I will have MCS 11, fastest available data rate achievable on AX. When it's rainy, a little bit humid, then I will go down to MCS 10. And when I say humid, we are at a disadvantage in the UK because it's humid all the time. And when it is, then the signal will be scattered by water particles in the air. And this will be reflected in lower SNR that will be reflected in lower data rate and MCS rate, unfortunately. That's it. So I think it's very practically achievable, 1024 QAM. Right? It's not a myth. You can do it.
No, we were together when we were doing these tests at your house, so I saw it with my own two eyes. It's achievable.
It is. Okay, so we have discussed different modulation schemes, starting with the BPSK 2 bits at a time, 1 bit at a time, going through QPSK 2 bits at a time. So the PSK, phase shift keying, it was using just phase as the physical phenomenon used to modulate ones and zeros into the air using Wi-Fi. And then we have discussed 16 QAM, 64 QAM, 256 QAM, and finally AX introduced 1024 QAM. So we know what it is. So we are using amplitude and phase to modulate ones and zeros. At the expense of the complexity, we can encode more bits at a time. And with QAM 1024, it's 10 bits at a time, up from 8 in QAM 256. Okay, so between 8 and 10, we are getting not a massive gain when it comes to throughput at 4 times higher complexity again. But it's still achievable. So it's a wonder, isn't it? Mm-hmm. What's next on the list? Do we have anything next on the list? Because we have discussed like how different modulation schemes, they affect the airtime. Mm-hmm. So let's maybe spend a second there. If your device has a very low SNR and is still associated to the access point, and on the same radio, BSSID, there are multiple different devices, stations associated with it with way higher SNR. And when these high SNR stations talk or receive data, it's very fast. So they have something to receive, it's like bam, and they've received that. They haven't spent too much time in the air receiving or transmitting data. But when your device, like 15 or 20 or 50 or 100 meters away from a radio, tries to receive or transmit data, it will take longer time because they will be using lower modulation schemes. They will have lower SNR, and they will make it slower for everyone because they will contribute to more airtime utilization. Mm-hmm. So that's the data rate of the data frames based on the modulation schemes used. Now, there is a common misconception about the data rates and airtime utilization and base data rates and what this means in this example. So guys, if you allow very low data rates, basic data rates like 1 meg on 2.4 and 6 megs on 5 gigahertz OFDM transmissions, it means that even if your devices, they are extremely close to the AP and they have very, very high SNR levels, they will still be sending all the protocol overhead. So around 25% of all the frames in the air, they will be sent in AX, of course. They will be sent with the lowest available allowed mandatory basic data rate. So the data frames will be sent very fast, but before the devices, they gain access to the medium or they associate to the access point, they will spend ages consuming the airtime to agree on how to transmit data, when to transmit data, before even transmitting that data. If you want to learn more about how devices gain access to the Wi-Fi medium, listen to our previous episode. Was it the previous episode when we've discussed the game? Or 2 episodes ago?
2 or 3 more ago, I can't remember now.
Okay, yeah, so that should be quite insightful. And this is all correlated, right? So the airtime utilization and the basic data rates and playing the game, DCF, CSMA, CA, and CCI and ACI and CCI with OBSS, it's all related. So now, after listening to our 4 solo episodes with Matthew that we have done over the last 2 months,
should have a really good theoretical understanding of how Wi-Fi actually works.
Mm-hmm. Exactly. Absolutely. Okay.
Right.
And I think that concludes everything that we had on the list for today. Anything else to add?
No, it certainly does, and I'm looking forward. I'm already thinking about that video that we're going to be putting together with going to a football pitch and taking some shots at a goal, recording some videos, and then correlating that to the different types of modulation and how accurate we've got to be with our EVM box. So keep an eye out for that one. We'll definitely try and do that.
But we'll have to, Matthew, we'll have to modulate the SNR, the increase in noise flow. So I think we will start sober, right? And this means like low noise flow, and then we'll have like 10 shots each or something like that. And then with every beer that we consume, we will be doing more tests, and I think our accuracy will be compromised by the fact.
That's how we simulate having a higher noise floor. Okay, good idea.
It's very practical approach, isn't it? It's fun and it's scientifically correct. So I don't dislike it. I like it a lot.
Okay, sounds fun. All right, well, thank you very much, Mac, for your time. It's been an absolute pleasure as always, and I look forward to seeing you on the next one. And I hope everyone enjoyed the talk about modulation and Wi-Fi.
Thank you very much, Matt. Thanks a lot, everyone, and we will see you back in 2 weeks' time.
Yeah, bye-bye.
Bye.